Good afternoon, everybody. Today, what I want you to take away from the session here is just some basic information about how to recognize what type of temperature probe, thermal well, and other peripherals that go around it, accessories, if you will, and be able to provide enough information to a manufacturer to accurately identify the part and get the correct replacements for those. The RTDs and thermocouples have dozens upon dozens of different configurations available, and it can get to be a little bit difficult to identify what all of those different features and things are. So today what I'm going to start out, we'll talk about RTDs first, thermocouples, and then we'll look at Thermowells and finish up with just a little bit on connection heads. So, like I said, there's a big mess. This is just some of the variety that you can see here. There's, in addition to the temperature probes, there's also the transmitters that can go with this. Variety of connection heads, whether they be explosion proof or just kind of a general purpose type thing. But it can be quite a confusing mess of stuff. Some of the terminology that gets tossed around, you'll see RTD, PRT, lots of abbreviations and things. So a PRT is a type of RTD. So it's a platinum resistance thermometer. It's one of the most common types of resistance temperature detectors. R0 be another question that comes up. You know, what is the resistance at 0 degrees C? Most of these are going to be 100 ohms at 0 degrees C. Some of the other kind of oddball types that you may run into are RTDs that are made with nickel wire or copper wire, and they may have a different resistance at 0. Nickel sometimes are 120 ohms at 0, and copper are 10 ohms at 0 degrees C. So those are things that are going to have to be looked at if you've got kind of an oddball type of RTD that doesn't fit into kind of the standard platinum resistance thermometer definitions. The temperature coefficient, also very important to identify this correctly. Sometimes it's called alpha, sometimes TCR, temperature coefficient of resistance. And the common types of PRTs are defined by these two standards, the 60751 and then the ASTM 1137. And then there's dual and single elements, and I get a few questions about this. So with a dual sensing element, it just means that there's two completely separate temperature sensing elements in the single probe, and that's typically done if you have a separate peripheral that you may want, like a local indication of temperature, and then the other sensing element would go off to a temperature controller, for example, or a chart recorder. There are also triple elements. I think we've even done some quads, and you know, those are convenient for if you just want to drill one hole in the pipe or the tank and get multiple outputs out of it. That's one way to do it. So those are just some of the terms that are going to come up. There are others, but these are just some of the more common ones. One of the first things to look at when trying to identify an RTD is the number and the color of the lead wires. There's either going to be usually 3, 4, or 6 lead wires coming out of the probe, and the color codes are going to vary a little bit. With a 3-wire single element probe, it's typically going to be 2 reds and a white. And then with the duals, it's going to be 2 reds and the white, but in addition to that, you're going to see a pair of green wires and a black. And then, of course, there is an exception. The color codes have changed a little bit with the two standards that came out, and these are probably 15 or 20 years ago that these standards came out and defined color codes. And so you'll see the ones that I just mentioned, but you'll also notice that the green wires here are now yellow, and manufacturers are starting to switch over to these color codes, and so you may end up seeing black and green, or it may be yellow and black. So at any rate, they both kind of define the same thing. It's just time hasn't caught up to some of the other manufacturer color coding definitions. The next test to do would be some electrical tests. So if we've identified this thing that, you know, it's got 2 red wires and a white, next thing to do would be just to check the resistance in an ice bath. And this is the most accurate test. It's also a really good test just to verify the function of the probe, just to make sure that it's still accurate and going to be reading correctly for you. And this will be, should read 100 ohms, and depending on what classification of interchangeability it has, it might be the Class A, which would have this plus or minus 0.06 ohms, or the Class B would be plus or minus 0.12 ohms. And if it's outside of those, but pretty close, it just means that the probe has probably drifted a little bit. But it would still help identify that this has an R0 of 100 ohms. Occasionally, you may run across an RTD that has a 200 ohm or a 500 ohm resistance at 0 degrees C. It doesn't happen very often, but there are still a few of those out there. So that's why this is a good check to do, just to verify that it is in fact a 100 ohm sensor. When this resistance is being measured in an ice bath, you know, if you have access to an ohm meter that has a lead wire compensation input, that's great. If not, and if you just have the regular little handheld volt ohm meter, what you want to do is manually eliminate the lead wire resistance in the probe. And the way to do that on a 3-wire or a 4-wire also would be just to measure the resistance of the 2 red lead wires, and then subtract that from what you measure between the white lead and just one of the reds. And that will give you just the resistance of the platinum resistor. If you include the lead wire resistance, they're all going to be over 100 ohms at 0 degrees C. So you need to either, you know, use a lead wire compensating ohm meter, or just do the manual method. So I don't know if we have any questions yet, Jeff, or if we just keep plowing ahead here.
Maybe one of the questions, or maybe a point of clarification, is just you pointed out some duals, and I know you're moving on to the thermocouple now, but how can you tell if maybe you have a dual thermocouple, so it's got 4 wires, versus a single 4-wire RTD?
Well, that's going to be another one of these electrical tests that we have to do. Usually the ice bath will tell you right away if that's the case. You can also do some continuity tests, and I think we can get into that right here. With thermocouples, one of the ways that we can help identify these is just by the color of the lead wires. And now these are going to be a little bit different than the RTD colors. Unfortunately, like a type J thermocouple is going to have 1 red lead and 1 white lead. So if you have a 2-wire RTD, which is quite rare unless it's in some kind of an HVAC type building system, it may have a red and a white lead. But the way you could help identify that would be that in a type J thermocouple, one of the leads is iron, so it's going to be magnetic. A type E thermocouple will have a purple and red, and you can't really see on this photo real well, but it looks kind of like both leads are kind of brown, but one of them has a little purple stripe on it. So sometimes you got to take a little closer look to actually see what the color code is on these. Type K is going to have a yellow and a red lead. And then with the types R, S, and B, these are platinum rhodium alloy thermocouples used for high temperature measurements, and that's why these are all in ceramic. And they put these little crimped ends on here because the platinum wire is quite fragile. So these are fairly readily recognizable. This manufacturer even writes right on the ceramic, and this appears that it was put on with a little kind of a magic marker type thing, so it may disappear after the thing goes up to temperature, but you know, at least initially they've got some way of identifying it, and they've identified the one lead wire with a little plus sign. It's most of the time when you run across these, they're not going to have any kind of color coding on the lead wires just because the materials that are used don't lend themselves to have any kind of a dye pigment put on it. Some of the other things, you know, I mentioned the type J, the positive lead is iron, so it's very highly magnetic. A type K, the negative lead is just very slightly magnetic. Type T thermocouples, you're going to notice that one of the leads looks just like copper wire because that is in fact what it is. And the type E and type N, those are a little tougher to identify. You usually just have to kind of go by the lead wire color codes. The IEC standard has a little bit different color coding. Black and white's a type J, and you go down the list here and you can see what, you know, we've got, in fact, if I just go back here, we see type N is orange and red, and now it's changed to pink and white. So these, of course, are going to be kind of hard to remember, but a little Google search will really quickly show you what those lead wire color codes are. You should be able to match it up fairly easily. The next thing to do with these thermocouples would be just a simple electrical test. And this is just to determine if it is in fact a thermocouple and not an RTD. If you just go between the leads, you're going to get less than an ohm of resistance typically. And then the next test to do would be to determine if it's an ungrounded or a grounded junction. And this is a continuity check between the lead wires and the probe sheath. And of course, with a grounded junction, you're going to get continuity. If it's ungrounded, there's not going to be any continuity. And that's this grounded or ungrounded junction is one of the options that you'll need to specify for a replacement thermocouple. Now we get into kind of the physical description of the probes, and some of the more common things to look for is it's spring-loaded. If it's going into a Thermowell, spring loading is really important to keep the probe firmly bottomed out in the well so that it doesn't rattle around if there's any kind of vibration. It also helps a little bit with heat transfer so that you have that solid metal-to-metal contact with the Thermowell. There are some different types of spring loading. This type has an internal spring inside of this threaded housing. This one's external. This is just a little bayonet lock cap that this probably fits into a little adapter piece that's got a little peg on it that this piece locks into. Another type, and this is kind of a European style or DIN style if I've heard it called. And the spring loading comes from either the springs on the screws that mount it into a connection head, or there may be a spring on the probe sheath. So these are some of the things that you'll need to identify when looking for a replacement probe. Now, direct immersion style, these are going to be a little bit different. We have here, this is a welded housing. Looks very similar to the other one, but you can see that it's all sealed up and welded. And of course, we have the sanitary type fittings. This is another fitting that was patented by Ingold numerous years ago. And these are typically used in bioreactor vessels. More commonly for O2 pH meters, we'll use these kind of probes, and manufacturers have adapted the fitting to temperature so that the same ports in the tank can be used for temperature as well as the pH and O2. And then finally here, another direct immersion style probe, and this uses a compression fitting as the process connection. Things to specify here would be the thread size, and these are typically an NPT thread. Along with that, the probe diameter so that the correct compression fitting gets specified. And then there's options for if you need a readjustable fitting, we could put a Teflon ferrule in with the compression fitting, or if it's just a one-time set it and leave it to be a stainless steel ferrule. A lot of manufacturers will put a serial number on the probe, and these are important for tracking the calibration of the probe. So always look for a serial number, and a lot of times it'll be right on the probe sheath if it's the type that goes into a Thermowell. If it's a direct immersion style, it's going to be on some of the non-wetted surface or the external parts of the sensor like this, right on this little connection head mount here. There's a lot of numbers there. The top one says SN, so you have to assume probably that means serial number. And the other numbers are probably heat numbers for the wetted surface materials to help identify the material certifications that specify the chemistry of the metal that was used. So with that,
yeah, we got a couple questions. So one of them had to do just with, actually I think both questions had to do with thermocouples. And there's just a question here as to temperature range of each type. And I don't think that's probably in your presentation, Bill, but if off the top of your head you could give a range of the different types of thermocouples, that would be, I think that's what they're looking for.
Oh, a little memory test here, yeah. Huh? Okay, well the Type T has the lowest temperature rating, and I think it goes to about 750 Fahrenheit. Type K would be, you know, the specs say like it's 2050, but I typically don't like to use them much past like 1850 Fahrenheit. They tend to drift really fast when you get too high in temperature. The Type J would be about 1500 Fahrenheit, and same for the Type E. The Type T, it can also be used below zero, or it's commonly used below zero. It also has the feature of having the best accuracy of any of those base metal type thermocouples. So that's, I guess, right off the top of my head, that's kind of my best recollection of what the temperature ranges are on those.
Perfect. And we do have on our website, you can find the you know, the exact ranges, and if there is a specific question on the ranges, we can you know, give us a call or shoot us an email, and we can get you the specifics. Another question on the thermocouples is, what are some of the applications for grounded thermocouples versus ungrounded thermocouples?
Well, typically, probably the most common is the ungrounded. Sometimes the electronics that are reading that low voltage coming from the thermocouple will need to have either a grounded or an ungrounded for a variety of reasons. One of the most common ones is that with the ungrounded junction, it isolates the thermocouple from any miscellaneous electrical noise that might be flying around and make its way back out to your instrument. The grounded junction is useful if you need really fast response time. It's slightly more durable because those lead wires are welded right into the probe tip, so they really can't move around much. Whereas with the ungrounded junction, the two thermocouple wires are joined together and then some insulation is packed around them. So there's a potential there that if you got really severe vibration, they could move, and over a long period of time, they could fracture and come apart, cause an open circuit. Those are just some of the features of those two.
All right, perfect. Thanks, Bill.
So, Thermowells. There are a bunch of different kinds of Thermowells, and usually Thermowells, they typically don't wear out. So, but the probes that are in them sometimes do. Or and one of the more useful dimensions to get out of the Thermowell is the bore depth. And with that bore depth, we can go ahead and specify the correct length of probe to fit in there with whatever accessories that you want to go along with it, whether it's an extension between the Thermowell and the head, or different kinds of heads or different kinds of probes. But if we have that bore depth number, that's by far the most useful of anything that you can provide to an RTD or thermocouple manufacturer to come up with the right length probe to fit that particular part. Because the lengths can get to be very confusing because you've got spring loading. Sometimes a direct immersion style probe is required to get a secondary seal with something like that. And it might be a probe that has just a connector on it rather than a connection head, so just be an electrical connector. But all of these are going to have different ways of that manufacturers specify the probe length, and you can try and outguess them by saying, well, the overall length of the probe is 12 inches, but that can mean absolutely nothing if different accessories are chosen. So get the bore depth. It's very easy to do. Take a piece of wire, whatever, shove it down inside the well, and just mark this bore depth A length and measure it. And with that, we can get the right size probe. There, did I emphasize that enough, Jeff?
I think so. That's the key is the bore depth, and the easiest way to do it, as Bill said, go ahead and leave all your extensions and unions, whatever. You can leave it right on there, and you can actually just put a piece of wire down inside the bore when it bottoms out. Kind of measure, put your finger on that piece of wire, pull it out of the Thermowell, put it down next to a ruler, and measure it. That way we know exactly how far we need to get into the Thermowell. And different manufacturers do have slightly different ways of measuring these things, but the bore depth is always the same. So if you give it that number, then the rest can be worked backwards to make sure we get you what you need.
Yeah. So, but if we have a case where Thermowell did fail and we need to specify some new dimensions, there's the U dimension. That's the actual immersion length from the very tip of the well here back to where the threads or the flange starts. If it's a tapered stem, we'll have, typically there's some default numbers for the taper, but if you have a specific requirement, this Q1 and Q2 dimensions can be specified. But the U and the leg length, the material, and the stem diameter, those are kind of the four most common parts or parts of a thermowell that you need to specify. There's, in addition to this, there's a default number that is necessary for threads or a flange, and a wrench hex. And then in addition to that, if you have like insulation around a pipeline or a tank, you may want to specify a lag extension, and that's defined by the T variable. Typically, the instrument connection is a 1/2 inch NPT. This is probably the most common, covers about 98% of what's out there. The other thing would be the bore diameter. Most of these are 0.26, so that they will accept a 0.25 inch or a 1/4 inch diameter temperature probe. And again, the bore depth down here is something that if you're specifying just the thermal well, if you give us the U dimension and the T and whatever thread type, you don't need to specify a bore depth. It's just going to be those dimensions, the U and the T is what's really required to come up with the thermal well. And then we need to know what type of process connection, whether it's threaded, and these are going to be like a usually an NPT. It may be the kind of the British version, the BSPT thread, but it'd be some kind of a tapered thread. And then whether the stem is, this happens to be a stepped or a reduced tip stem. This one shows tapered, and this has an ANSI. It's a, what is that, the American National Standards Institute, something like that. An ANSI pipe flange and a tapered stem. And this will have a rating on it, so it'll have a size, like it might be, this one happens to be, I believe, 1.5 inches. And then it'll have a class, like a 150, 300, 600. And that's usually stamped right on the edge of the well. And I think if you look close at this, you'll see some of that information just stamped right on the edge of that flange. Another process type is just a straight weld-in. This style is typically welded into tanks or other vessels. Then a socket weld. More commonly, these will probably get welded into a pipeline, into a little socket that's welded to the pipe, and these drop in, and then you can weld it into that socket. I mentioned the Ingold type fitting earlier, and then like a direct immersion style probe, and this has been adapted to a thermal well also. This also has a 1/2 inch NPT female threads to accept a temperature probe, most likely a 0.26 diameter bore. Example here of a straight stem with a hygienic ferrule. And then the Van Stone, which is another type of thermal well that has a backing flange. So this would drop in and mate to another flange, and then there's another flange that goes over the top of this with some bolts that suck it all together and provide the seal. So lots of different types. Now I mentioned that the NPT was a real common instrument connection. This particular thermal well has the hygienic ferrule as the process connection and the instrument connection. And this is nice if you need to frequently remove the probe for calibration, because a little hygienic ferrule or tri-clamp fitting is pretty easy to take apart. Loosen the clamp, pull the probe out, and you're all set to go. And then kind of a hybrid style of Thermowell. This one happens to be mounted in a sanitary elbow, which is a real good method to measure temperature in a small diameter line. Like if it's half inch on up to about 2 or maybe even a 3-inch sanitary tubing. This is a real good method to measure temperature. And so this is set up with the flow coming directly at the tip of the Thermowell. So some things that you would need to specify here would be the fact that, well, it's the elbow style. And then if you need the weld ends, or if another option would be a hygienic ferrule, if you want to be able to just clamp this in place and be able to remove it for cleaning the system or for whatever reason. And this shows a threaded NPT connection for the temperature probe. There's also a hygienic ferrule option for this particular style. And on all the Thermowells, you're going to most likely notice some numbers, and these are going to be the heat numbers, and they really don't help identify the type of Thermowell or anything it is. It's just going to, if you're trying to get a replacement, it's just going to let the manufacturer know that, yeah, this, the heat numbers and the material chemistry was traceable, and these are kept on file. It's really not going to help identify the Thermowell, so only for the material certification. And another example, this one, the 304 probably means the Thermowell was 304 stainless, and that was the heat number for this particular one. And if we really don't know what the material is, you can do a kind of an X-ray fluorescence type thing, and typically called positive material identification, or abbreviated as PMI. A lot of manufacturers can provide this service. You send them the well, we'll shoot it with the gun and see what the material is. And it's not going to get the full chemistry, but it'll tell you if it's like 304 stainless or 316 or any number of other possibilities. But that's one way to help identify it. So I don't know if you want to...
Yeah, Bill, before we move on to connection heads, just a reminder, a question came in about Thermowells, and in all cases, whether you're using an RTD or a thermocouple, either one can go into a Thermowell. So there is, the fact that you have a Thermowell doesn't identify it as one or the other. You still would have to go through the earlier test to verify whether you have an RTD or a thermocouple. Sometimes there comes some confusion because you can order a complete assembly, which is a sensor and a Thermowell together. But when it comes time to replace, you don't need to replace the whole thing. You just need to replace the sensor portion of it. So if you do have the number of the assembly, oftentimes that helps in being able to identify exactly what it is that you have or what you need. Or in the case that you don't have the number of the assembly, then you can always start by getting the bore depth of the Thermowell and then describing what the sensor looks like and what it does. Also, I will tell you, if you can take a picture of it, that helps immensely as well. Take a quick photo and send it to us. And as they say, a picture is worth 1,000 words. So if you can show us the sensor, the length of the sensor, number and color of the wires, that helps in identifying exactly what you have.
Yes, exactly. Good stuff. The rest of the outside of the part usually terminated with some kind of a connection head or a connector or extension cable. And on the connection head, lots of different materials. There's explosion proof, there's kind of general purpose, plastic, aluminum, cast iron, stainless steel. Sometimes these are a little hard to identify, especially if it's a painted head. You may have trouble trying to figure out just what the original material is, if in the case where you're trying to replace it. The hazardous atmosphere rating, pretty important. If you've got explosive gases or dust around, that when you're purchasing a replacement temperature assembly, that you identify what those materials are that are the hazard, and that way we can help pick the right assembly type and the right approvals that go along with that particular environment. A lot of times the connection heads will have labels on it, and like this one shows Class 1, Division 1, Group A, B, C, D. Well, that's like acetylene gas is the most explosive atmosphere, and maybe you've got a situation where you only have like some dust floating around part of the time. Well, that's Class 1, Division 2, or whatever the numbers are. You might be able to get by with a little different connection head setup. It doesn't have to be quite as stringent or rigorous as what this one shows. So more information to help the manufacturer get you exactly what you need. This is another example of a label. This happens to be factory mutual for Canada and US, and it's approved for Class 1, Div 1, and again, this is Group A, B, C, D. Inside the connection head, you may have a transmitter, you may have an indicator, or maybe just a terminal block. Take a peek inside and see what's in there. There's quite a variety of these also. And as Jeff mentioned, if you're really not sure what's in there, take a picture of it, pull the cover off, take a photo, send that along. That can be a huge help to identify the assembly that you have. So with that, I know we've gone through all of this stuff here, and then if you can't do some of the tests, or if you just don't really know what it is, snap a photo. Send a lot of photos. Take the cover off the connection head, take a photo of the inside so it shows the lead wires, the number and the color, terminal block, transmitter, show the process connection, and throw a tape measure down beside the probe and have have it clear enough so that we can see what the actual length of the probe is and get some idea of the connection size type, whether it's NPT or a flange, and then any kind of markings that are on the probe, taking a little close-up photo of what appears to be a serial number. Some of the older probes, I know I've seen the serial numbers get smudged up and pretty hard to see, but sometimes with a little guessing or based on the type of probe and the serial number, range, whatever, kind of figure out more or less what the part is and at least narrow down a lot of the options. As you've seen with these assemblies, there are dozens upon dozens of variations, and anything that can be done to help kind of narrow down the possibilities really helps towards getting the right replacement style parts to go with your system. So, and with that, I think we're about to wrap up.
Yeah.
And I guess if you have any more questions, send them in now and we can get to that. If not, feel free to give me a call, shoot me an email. You can also get a hold of us at our website. There's a feature there, and it comes to our info at email box, and then there's at least a couple of us that answer all of those daily, and you'll typically get an answer within 24 hours.
Okay, and as a reminder, if you do have any questions, we have a few minutes yet, so go ahead and type them into the Q&A or the chat box, and we'll try to get you an answer. Did want to mention one thing as Bill was talking about the serial number. If you do happen to have a burn sensor, just for your information, on our website, you can actually put in the serial number on our website, and it will tell you, it'll pop up what the model number is, what the part number is. So that's if you do happen to have a burn sensor, that's one good way of determining exactly what you have. 3 years. Yep, I think we've got 3 years of information. The last, actually, I think it's coming up on 4 years. But
yeah.
Yep, if you have something before that, you could give us a serial number, and we can look it up internally. We do have a couple questions. So here's an application question, Bill. When using an RTD in a Thermowell or just submersed in a solution, I got to scroll down here. Where half of the steel casing is exposed to the environment, will this have an adverse effect on the temperature reading?
Yes, is the short answer. It can have a big effect on it. With any temperature probe, whether it's thermocouple, RTD, thermistor, whatever, you're going to have some stem conduction. So it's going to have, the ambient conditions are going to have some effect on the measured temperature. Usually with like a 1/4 inch diameter probe, you need to have about 3.5 inches of immersion to get a good accurate measurement. And with a Thermowell, our testing has shown about 4.5 inches does a really good job. You know, and it's always more is better, but you do have to balance that with the strength of the probe or the well. If it's in a high flow situation, for example, if you get too much immersion, the high flow rate can cause the probe to, or the Thermowell to vibrate and cause the probe to fail. But yes, anytime you have a short immersion, you're going to see some stem conduction error come into play.
And another question kind of along those same lines, Bill, is if all you have is the pipe size and the process connection, is there a standard for the U dimension? Or in the case of a direct immersion, the L dimension?
You know, there are some kind of general, I don't know, rule of thumb around that. And, you know, I've seen, okay, you want a 1/3 of the pipe diameter as the immersion length, or a 1/2 or 2/3, or, you know, pick your favorite fraction. But really, you need to balance the immersion length and the strength of the well and the wake frequency characteristics of the Thermowell if it's in a pipeline situation. You know, because you can have an ideal immersion of like 6 inches for a Thermowell into a pipe, but if it's got a high flow rate and it's going to cause that Thermowell to vibrate and fail, you know, it just isn't going to work. So you need to shorten up that well so it does pass these wake frequency calculations. One of the other webinars talks about Thermowells and the wake frequency and strength issue, and how to go about selecting that so that it's not a problem. So I kind of dismiss a lot of the, you know, kind of the rule of thumb thing, like you need to have a 1/3 of the diameter immersed to get a good temperature reading. It's really more important that you pick an immersion length that is long as possible but still passes the wake frequency strength calculation. I also looked at another guy did a study on the temperature gradients within a pipe, and a lot of times there's a lot of turbulence going on, and you're going to get some many different temperatures throughout the cross section of that pipe. You know, if you've got perfectly laminar or really well mixed flow, then there's a lot less of that going on. But I was really surprised at how much variation there was within a a pipeline when you don't have real good mixing of the fluid. So, yeah, it's just balance the immersion length with that wake frequency strength calculation.
I think the other component, as Bill mentioned a little earlier, was just on you do want to make sure it's far enough in the process, but it doesn't have to actually go halfway into the process where you have a 24-inch long Thermowell, something like that. But also if you're toying with the idea of I can only get this, I can only get an inch of immersion, then you start to have potential issues with stem conduction error, and so you always want to balance those two. So did just want to mention that this session is being recorded, and we will post it on our YouTube page. So if you go to YouTube and type in RTDology, it'll pop up our channel, and you can go ahead and see the whole presentation there. We usually get that on there within the next 24, 48 hours. That'll usually be on there.
I'll try to get that on there probably by tomorrow morning sometime. It takes a little bit of time to upload it and stuff. So again, if there are no other questions, I want to thank you very much for attending. We look forward to seeing you at our next session. We will have the lineup for the next year will be coming out shortly. So look for that email, and we hope to see you at a future session.